The power grid across the western and central territories of Russia entered a state of cascading failure after a sequence of technical malfunctions and abrupt voltage collapses that originated within the unified dispatch system controlling high-capacity substations. The first signs of instability were registered along the Volga and central industrial corridors, where simultaneous disconnections of transmission lines overloaded secondary circuits, triggering a chain of automatic shutdowns across multiple administrative regions. Within hours, the blackout extended beyond the regional level and reached the federal grid balance, cutting electricity supply to major population centers including Moscow, Tver, and parts of Nizhny Novgorod. The transition from localized disruption to systemic paralysis occurred with exceptional speed, revealing the absence of redundancy in Russia's internal energy management infrastructure. The Unified Power Dispatch Center attempted to reroute energy through reserve transmission corridors. However, the automatic load-shedding systems failed to stabilize frequency. Emergency operators initiated manual intervention procedures, disconnecting industrial consumers and halting rail electrification in order to preserve generation assets from overheating. Despite these measures, voltage levels continued to fluctuate unpredictably, indicating deep instability within transformer synchronization circuits. The disconnection of key substations isolated entire districts from the central grid, leaving them dependent on limited local generation capacity insufficient to sustain basic civilian demand. In Moscow, the metropolitan grid collapsed in successive layers. Peripheral districts lost power first as protective relays tripped in response to regional overloads, followed by the inner industrial belt and, finally, the administrative core. Street lighting, metro operations, and digital communication hubs ceased functioning almost simultaneously. Backup diesel generators in government buildings activated but provided only minimal illumination and partial restoration of communication services. The capital, long considered the most secure and heavily fortified in infrastructure terms, experienced total darkness for the first time in its post-Soviet history. The blackout's timing coincided with heightened public sensitivity to infrastructure vulnerability. Urban residents accustomed to constant illumination and digital connectivity suddenly found themselves isolated. Mobile networks lost coverage as base stations exhausted their backup power, and internet nodes dependent on external substations ceased transmission. Within minutes, the social sphere transformed into an environment of uncertainty. High-rise elevators stopped, traffic systems froze, and electronic payments became inoperative. The silence of official communication channels amplified confusion. Government media delayed statements, awaiting verification of situational data, but the absence of public information created the perception of concealment. Regional administrations attempted to activate municipal emergency grids, yet many of these systems had been repurposed for wartime redundancy and lacked direct civilian control. Diesel reserves were either insufficient or located in depots inaccessible due to power-locked security gates. Hospitals and command centers prioritized critical systems, leaving residential zones in extended blackout. The contrast between heavily guarded administrative sectors that retained partial lighting and dark civilian districts produced visual evidence of division between state and population, intensifying the perception of crisis. The blackout extended its influence beyond the technical domain. Rail transport halted as electric traction systems lost current. Airports delayed departures and landings while switching to auxiliary runway illumination. Pipelines and fuel depots depending on electric pumps experienced flow interruption, forcing temporary suspension of fuel transfer operations. Industrial output declined to a fraction of nominal capacity as smelting, chemical, and assembly lines were shut down to prevent equipment damage. The economic implications of even a single night of total power loss in the capital reverberated across supply chains that connected production centers in the Urals with markets in the West. The strategic significance of the event exceeded the scope of technical malfunction. Power generation and distribution represented the foundation of both civilian stability and military readiness. Its disruption, regardless of cause, symbolized systemic fragility. The blackout exposed structural dependence on centralized control and the absence of autonomous regional energy clusters capable of maintaining continuity under emergency conditions. In the darkness, Moscow stood as a demonstration of how concentrated infrastructure could become a single point of failure for an entire nation. The collapse of the Russian power grid followed a precise technical pattern that revealed deep structural weaknesses long concealed beneath official reporting. The unified dispatch system, which governed transmission coordination from the Baltic to the Urals, depended on synchronized switching algorithms designed to balance load across continental distances. When the initial surge occurred in the Volga cluster, automated balancing failed to compensate, and the protection relays misread the current variance as a short-circuit event. The system executed automatic isolation, cutting transmission between regional nodes and severing power flow to the central axis feeding Moscow. This self-protective procedure, intended to localize damage, instead cascaded through interlinked lines, creating a sequence of disconnections that no operator could override without destabilizing adjacent networks. The depth of the malfunction revealed an administrative flaw. The central dispatch had consolidated all decision-making authority in a single monitoring hub near Moscow, which processed grid telemetry through an obsolete software interface. Modernization plans drafted in previous years remained partially implemented. Several regional substations still operated under legacy Soviet-era control circuits without digital redundancy. These systems required manual calibration, but most qualified technicians had been redeployed to defense-related industries. As a result, when the frequency deviation exceeded permissible limits, no personnel were available to execute manual rebalancing. Remote systems attempted to stabilize voltage by drawing reserve capacity from auxiliary plants, but those plants were operating on restricted fuel due to prior rationing orders. Maintenance data showed that the majority of power transformers within the affected corridor were already past their designed service life. Inspections had been postponed to conserve budgets, and the cumulative degradation of insulation systems rendered them vulnerable to thermal stress. When sudden load reversal occurred, dielectric breakdowns caused transformer fires in several nodes, forcing emergency operators to disable entire sectors. Fire suppression crews reached only a fraction of sites due to paralyzed traffic and loss of radio communication. By the time power engineers re-established partial connectivity, the grid's structural integrity had already collapsed beyond immediate recovery. The absence of distributed microgrids compounded the effect. Urban centers lacked autonomous generation clusters that could isolate from the main grid and sustain essential services. In contrast, Ukraine's network, decentralized after years of reconstruction, demonstrated resilience under similar conditions, maintaining supply through modular units even during high-intensity attacks. The Russian configuration remained hypercentralized, making it efficient during stable conditions but catastrophically fragile under stress. Once the principal frequency regulator in the capital disconnected, the rest of the network followed automatically, obeying coded sequences that prioritized asset protection over service continuity. Decision-making during the initial hours remained paralyzed. The Federal Energy Ministry delayed issuing emergency protocols until data validation was complete, while regional dispatchers awaited central authorization to reconnect lines. Without confirmation, they kept systems offline to avoid triggering chain reactions. This bureaucratic rigidity prolonged the blackout. Engineers within independent energy enterprises attempted to synchronize local generation to support hospitals and metro ventilation systems, but the lack of standardized connectors prevented integration. Diesel generators supplied power to critical nodes, yet their fuel reserves were calculated for temporary outages, not extended failure. Within half a day, several backup systems exhausted reserves entirely. Efforts to conceal the scope of the failure began immediately. Official statements described temporary disruptions caused by scheduled maintenance. State-controlled media avoided terms such as collapse or blackout, replacing them with neutral language implying planned downtime. However, absence of light in the capital rendered these narratives implausible. Residents documented total darkness across multiple districts and circulated recordings through private channels. Attempts to block uploads proved ineffective, as users employed virtual private networks and satellite messaging applications to bypass domestic firewalls. Within minutes, images of Moscow's dark skyline appeared across foreign media platforms, contradicting official silence. The disparity between state messaging and public observation widened into mistrust. Citizens demanded explanations, but press briefings remained postponed pending authorization from upper administrative levels. Information vacuum generated speculation of sabotage, cyber attack, or concealed infrastructure accident. Online discussions attempted to correlate the event with prior electrical disturbances, exposing fragments of previously suppressed incidents in Siberia and the Far East. This informal information network became the primary source of situational awareness for millions, while the government's communication structure remained immobilized by its own censorship protocols. Strategically, the blackout transitioned from a technical emergency to an information crisis. The inability to control narrative flow eroded administrative authority and demonstrated how infrastructure failures could destabilize perception as effectively as physical attacks. The state's reliance on secrecy to maintain the illusion of stability produced the opposite effect. Each hour without official transparency increased public anxiety and international scrutiny. By the end of the first day, Moscow's darkness had become both literal and political, reflecting a governance system unprepared for the intersection of technological fragility and information exposure. The blackout propagated rapidly through urban and suburban networks, leaving millions of residents without power, lighting, or heating. Residential high-rises lost elevator service, forcing occupants to evacuate via stairwells, while traffic signals failed across arterial roads, producing gridlock that immobilized emergency vehicles and logistics convoys. Hospitals and emergency medical facilities switched to backup generators, but only a fraction of units remained operational due to limited fuel reserves. Industrial facilities dependent on electric traction or continuous process systems shut down entirely, halting production and risking equipment damage. Water supply and pumping stations reliant on electric motors experienced partial shutdown, prompting municipal authorities to distribute bottled water and emergency rations where possible. Simultaneously, communication infrastructure collapsed. Mobile networks operated at reduced capacity, with many base stations going offline as backup power depleted. Internet access was intermittent, forcing residents to rely on satellite messaging or peer-to-peer networks to coordinate basic services. Social media quickly became the primary outlet for information, generating widespread documentation of the blackout. Citizens posted images and videos showing completely dark districts and frozen transport systems, while online speculation proliferated regarding the cause, ranging from system failure to deliberate sabotage. Panic spread in digital spaces faster than authorities could respond, amplified by the contrast between Moscow's darkness and Ukrainian cities' continued energy resilience amid conflict conditions. Urban logistics suffered immediate paralysis. Fuel distribution points suspended operations when electric pumps failed, constraining the availability of gasoline and diesel for personal and official vehicles. Rail transport ceased due to the loss of electric traction, and airport operations were reduced to emergency lighting protocols, delaying both commercial and cargo flights. Industrial hubs in peripheral districts halted smelting, assembly, and chemical processes, generating cascading economic losses. Essential deliveries, including food and medical supplies, were delayed or rerouted through improvised means, while municipal authorities struggled to coordinate emergency response without reliable communication and transport networks. Official communication remained sparse and delayed. Government statements framed the event as localized technical disturbances and urged calm, but the scale of observable disruption contradicted this messaging. Urban residents witnessed widespread darkness, gridlock, and frozen services, which intensified the perception of concealment or incompetence. Social media narratives gained momentum, documenting failures and comparing the capital's vulnerability to Ukrainian cities that continued to maintain power despite cyber attacks and military strikes. The dissonance between official assurances and visible reality accelerated public anxiety, creating a dual crisis of infrastructure and perception. Emergency responders faced operational strain. Without predictable electricity and with traffic immobilized, fire, police, and medical units could only respond selectively to incidents. Mobile command vehicles equipped with satellite communications became critical coordination nodes, yet their limited numbers were insufficient for citywide coverage. Engineers attempted to stabilize sections of the grid by activating isolated generation units, but the scale of disruption exceeded the capacity of local reserves, leaving many districts in darkness for extended periods. The blackout's impact extended to strategic installations. Ministry buildings and military command centers relied on backup generators, but reduced capacity forced prioritization of essential systems only. Railheads and fuel depots lost power, disrupting supply chains for both civilian and military assets. Data centers and digital archives operating without full redundancy experienced shutdowns or degraded service, raising risks of information loss or corruption. The operational tempo of state logistics slowed markedly as power-dependent systems remained offline. The social effect became apparent in public behavior. Residents reported unusual crowding at fuel stations and convenience stores as panic buying emerged, while private networks disseminated safety instructions and coordination guidance. Comparisons with Ukrainian resilience during similar attacks underscored perceptions of Russian systemic fragility, highlighting the vulnerabilities of centralized energy and command infrastructures. In urban districts where street lighting failed completely, citizens improvised illumination with candles and vehicle headlights, while surveillance and security systems lost real-time monitoring capability, creating both practical and psychological effects. The initial consequences of the blackout demonstrated how technical failure could propagate into social and administrative crises. Total power loss in Moscow and surrounding regions incapacitated transport, communication, and essential services, while the absence of timely, credible official communication generated public uncertainty and social unrest. The contrast between Russian vulnerability and Ukrainian operational continuity emphasized strategic weaknesses in infrastructure redundancy and emergency preparedness. The city's paralysis revealed that centralized systems, while efficient under normal conditions, were acutely sensitive to cascading failure, producing consequences far beyond the electrical domain. In response to the expanding blackout, municipal and federal authorities attempted to implement emergency measures, but systemic limitations hampered coordination. Regional energy centers activated contingency protocols, manually switching circuits and attempting to isolate functional sections of the grid, yet the network's interconnected design prevented selective restoration without triggering additional automatic shutdowns. Backup generation units at substations were limited in capacity, forcing prioritization of essential services such as hospitals, government buildings, and transportation hubs, while residential districts remained largely without electricity. The uneven allocation of power created visual and functional disparities across the city, further amplifying public perception of disorder. Transport infrastructure responded under duress. Metro services were suspended in all affected zones, leaving tens of thousands of commuters stranded within stations or along lines. Road traffic became heavily congested as signal lights failed, producing bottlenecks at intersections and critical arteries. Emergency vehicles relied on improvised routing and limited radio communication, navigating streets that had become unpredictable due to both gridlock and the absence of street lighting. Rail transport of goods experienced halts when electric locomotives lost power, forcing manual inspection and isolation of train segments. Airports restricted flights to essential operations only, with runway lighting dependent on temporary diesel-powered units, creating significant delays in cargo and personnel movement. Civil defense and emergency services were mobilized to maintain minimal operational functionality. Security and fire brigades established temporary command posts using mobile communications and satellite phones, prioritizing critical incident response. Engineering units deployed to restore grid stability focused on repairing or bypassing damaged transformer stations and redistributing load through isolated substation clusters. Fuel convoys carrying diesel to support generators were escorted by police units to prevent interference and ensure continuous operation of vital services. Despite these measures, the speed of restoration lagged behind the pace of demand, leaving large populations without functional electricity for extended periods. Simultaneously, government communication channels were overwhelmed. Attempts to broadcast information through traditional media outlets were constrained by power outages in transmission stations, while digital communication networks suffered from both congestion and intermittent service. Official narratives emphasized technical failure and reassured citizens of rapid restoration, yet the observable reality of total darkness across major urban districts contradicted these statements. Social media platforms, operating intermittently via mobile networks with battery-limited devices, became primary sources of information and coordination, with content documenting both infrastructure failures and improvised local responses. The operational logic of the blackout revealed systemic vulnerability in Russia's centralized energy architecture. High dependency on a few major transmission corridors and the concentration of control at single dispatch hubs meant that failure at one node could cascade to affect entire regions. Manual intervention proved insufficient without real-time telemetry, as personnel were either unavailable or unable to respond quickly to the complex sequence of faults. The lack of distributed microgrids, decentralized substations, and regional redundancy left the network susceptible to total collapse once automatic protective mechanisms were triggered. Military and strategic installations adjusted to the blackout environment by shifting reliance to isolated power units and independent communication networks. Command posts prioritized internal power generation and limited operations to essential functions. Certain units experienced operational pauses due to delayed resupply of electrically dependent infrastructure, while air defense, rail transport, and logistics operations faced slowdowns until stable power and communications could be re-established. Critical decisions regarding allocation of remaining energy were made based on immediate operational priorities, often leaving civilian sectors without support. The blackout, although initiated by technical malfunction, functioned as a stress test of urban resilience. Civil authorities and military services demonstrated partial adaptability but were constrained by rigid centralization and lack of autonomous operational nodes. Citizens improvised solutions, including using personal generators, candles, and vehicle headlights, yet these measures could not compensate for systemic failure. The gap between administrative response capacity and social necessity generated localized disorder and amplified perception of systemic instability. By the end of this stage, the metropolitan area remained largely without reliable power, while emergency measures provided partial functionality for strategic infrastructure. The combination of disrupted transport, compromised communication, and uneven power allocation created conditions that could be exploited by actors seeking to influence both operational and social stability. The blackout's effects transcended technical failure, producing an emergent crisis in urban management, information flow, and citizen compliance, underscoring the fragility of hypercentralized energy systems. Authorities initiated large-scale recovery operations across affected regions, mobilizing emergency energy crews, mobile generators, and repair brigades to restore electricity to critical infrastructure. Teams focused on substations that controlled high-capacity transmission lines, attempting to resynchronize isolated circuits and prevent further cascading failures. Temporary load-shedding protocols were enacted to stabilize remaining segments, prioritizing hospitals, government facilities, water pumping stations, and key transport nodes. However, the fragmented condition of the network and the exhaustion of backup fuel reserves limited the effectiveness of these measures, leaving many districts in extended darkness. Rail and road transport received partial operational relief as temporary traffic management measures were introduced. Police and traffic control units coordinated manually to relieve bottlenecks at intersections and critical highways. Limited metro services resumed in some districts where emergency power allowed ventilation and lighting to operate, but most urban rail lines remained closed, stranding commuters and delaying logistics convoys. Airports restored minimal operations using auxiliary diesel-run lighting for runways, permitting only essential flights to continue. Fuel distribution networks gradually reactivated under escort, but delays caused by infrastructure failure and bottlenecks at terminals restricted throughput to industrial and residential zones. Technical teams attempted to isolate failed transformers and reroute energy through less damaged corridors. Emergency generation units at local substations were synchronized where possible to feed hospitals, water stations, and government offices. Industrial facilities partially restarted by switching to isolated generator capacity, yet production lines requiring continuous power remained offline, producing economic stagnation across multiple sectors. Simultaneously, communication networks received limited restoration as base stations were powered via temporary generators and satellite uplinks, allowing partial mobile connectivity and resumption of internet access in certain neighborhoods. Despite these efforts, public perception remained critical. Social networks and messaging applications became primary sources of situational awareness, documenting ongoing outages and creating viral narratives highlighting systemic vulnerability. Images and videos of darkened streets, immobilized transport, and stalled industrial facilities circulated widely. Rumors of sabotage or deliberate disruption fueled panic, while comparisons with Ukrainian cities' resilience during similar attacks emphasized Russia's infrastructural fragility. Authorities continued to suppress full disclosure of the blackout scale, which increased speculation and undermined confidence in official information channels. Coordination between federal and regional agencies remained constrained. Many municipal energy offices lacked autonomy to act without central authorization, delaying interventions in peripheral zones. Engineers and repair brigades faced obstacles due to unclear jurisdiction over priority lines, access restrictions, and exhausted fuel supplies. While essential services regained partial functionality, residential areas experienced prolonged outages, compelling citizens to rely on improvised lighting, backup generators, and localized water storage. Emergency shelters and medical facilities relied on prepositioned reserves, which were insufficient to sustain operations citywide. The operational logic of the emergency response revealed systemic deficiencies in both technical design and administrative structure. Centralized decision-making slowed restoration, and the lack of distributed microgrids prevented rapid recovery for civilian populations. Reliance on centralized fuel depots and diesel generators limited the geographic reach of emergency power. While essential military and strategic installations maintained operational continuity through independent energy systems, urban populations experienced prolonged disruption, emphasizing the vulnerability of densely centralized infrastructure to sudden cascading failures. By the conclusion of the recovery attempts, partial restoration allowed essential services to resume in prioritized areas, yet large sections of Moscow and surrounding regions remained without reliable electricity. Transport, industrial production, and communications operated at reduced capacity. Public confidence was diminished, and social networks continued to circulate images and reports demonstrating systemic fragility. The inability to fully restore service highlighted both the technical vulnerability of the energy grid and the administrative limitations inherent in centralized decision-making, setting the stage for evaluation of broader strategic and societal consequences. Following partial restoration efforts, authorities implemented measures to stabilize the urban environment and prevent recurrence of systemic failures. Emergency management centers assumed permanent operational status, coordinating energy distribution, security, and civil logistics under a centralized command hierarchy. Substations, transformers, and high-voltage corridors were subjected to comprehensive inspections, and damaged components were repaired or replaced to re-establish minimal redundancy. Load balancing protocols were revised, and priority allocations formalized, ensuring that critical facilities including hospitals, command centers, and water supply systems maintained uninterrupted service during residual instability. Municipal authorities enforced restricted power consumption for residential and commercial sectors to relieve stress on the grid. Temporary curtailment schedules were applied, limiting electricity to non-essential services during peak demand periods. Diesel and backup generation units were stockpiled in strategic locations to provide continued operation of essential nodes, including railway junctions, airports, and metro ventilation systems. Emergency engineering teams remained on alert, capable of rapid deployment to address new outages or infrastructure failures. This approach effectively transformed temporary recovery measures into a structured stabilization regime, linking civil, industrial, and strategic systems under a coordinated response framework. Transport networks adapted to the new operational conditions. Rail lines resumed limited service under carefully controlled power allocation, while major road arteries continued to be monitored and managed manually to prevent congestion in areas where signal systems were offline. Airport operations were maintained at a reduced tempo, with emergency lighting and auxiliary fuel systems sustaining essential cargo and passenger movement. Industrial output recovered partially through isolated generator support, though continuous process operations remained limited. Coordination between municipal, federal, and energy authorities was reinforced, creating a layered command structure capable of prioritizing critical functions across overlapping sectors. The population adjusted to constrained conditions. Citizens relied on portable generators, improvised lighting, and communal resource centers to meet basic needs. Social networks became semi-official channels for information dissemination and local coordination, filling gaps left by official communication delays. Public behavior demonstrated adaptation to restricted infrastructure while simultaneously maintaining vigilance over governmental statements, creating a hybrid environment in which citizen networks effectively monitored and responded to ongoing instability. Strategically, the blackout forced institutional re-evaluation of infrastructure resilience and emergency protocols. Redundancy plans were revised to include distributed generation, independent microgrids, and satellite communication for command and control facilities. Contingency logistics were formalized to ensure fuel, food, and water distribution during prolonged outages. Military and strategic installations integrated lessons from civilian infrastructure failure, emphasizing the need for autonomous operational capability independent of centralized networks. The combination of technical correction, administrative centralization, and civil adaptation established a provisional equilibrium in which essential functions could be maintained while systemic weaknesses were addressed. By the conclusion of stabilization efforts, electricity supply to strategic, industrial, and critical civilian sectors had been partially restored. Residual outages persisted in less prioritized districts, and manual interventions remained necessary to prevent secondary failures. The emergency response created a formalized operational model for crisis management, linking energy, transport, and security under unified oversight. While the immediate crisis abated, systemic fragility persisted, and the population remained acutely aware of the vulnerability of the centralized grid, generating both social and operational awareness that would influence future planning and resilience measures. The blackout across Moscow and surrounding regions produced a multi-layered strategic impact, revealing vulnerabilities in infrastructure, administration, and public confidence. The immediate tactical outcome was the exposure of systemic fragility within the centralized energy grid. Cascading failures demonstrated that concentrated control of transmission and distribution created single points of failure capable of paralyzing large urban centers. Critical military and government facilities maintained partial functionality through independent generation, but reliance on centralized oversight left residential, industrial, and transportation networks highly susceptible to disruption. The operational imbalance forced authorities to reassess allocation priorities, emphasizing preservation of essential services over normalization for the wider population. The social and information dimensions amplified the crisis. Rapid dissemination of images, videos, and reports through social networks bypassed state-controlled media, generating public awareness and speculation that fueled both local anxiety and international scrutiny. Official attempts to suppress or manage information were ineffective against decentralized digital platforms. Comparisons with Ukrainian cities, which had demonstrated resilience under similar conditions, intensified perceptions of Russian vulnerability. This contrast influenced both domestic and foreign perceptions of governance capacity, highlighting the strategic implications of public confidence as a component of national security. Economically, industrial and logistical systems experienced immediate disruption. Production lines reliant on continuous electricity halted, chemical and smelting operations were suspended, and rail and air transport faced prolonged delays. Fuel depots and pipelines dependent on electric pumps ceased normal operation, restricting supply to both civilian and military sectors. The temporary paralysis of these systems illustrated the interdependence of infrastructure components and the cascading consequences of failure, emphasizing the criticality of decentralized resilience for national stability. Administratively, the event prompted structural reforms in emergency management and energy oversight. Load-shedding protocols, emergency fuel reserves, and independent microgrid deployment were formalized as permanent contingency measures. Regional energy centers gained authority to act autonomously within predefined parameters, while engineering and technical brigades were permanently positioned for rapid intervention. The security and military apparatus integrated these lessons into strategic planning, ensuring that essential command and communication nodes could operate independently of the civilian grid. The operational outcome reinforced central control over critical infrastructure while simultaneously exposing the need for decentralized robustness. From a strategic perspective, the blackout reshaped the balance of operational and political authority. Centralized control over energy and communications, once a symbol of efficiency, became a liability when disrupted, forcing authorities to prioritize resilience, redundancy, and operational segregation. Military and government facilities retained capacity to operate independently, but broader population centers remained dependent on state-managed restoration, creating a structural hierarchy of criticality. Long-term planning now required incorporation of distributed generation, autonomous operational zones, and contingency communication networks capable of maintaining both civilian and strategic functions under stress. The event also highlighted the interaction between technological failure and public perception. Lack of transparency and delayed official communication fostered mistrust and amplified the social impact, demonstrating that infrastructure failure could be as destabilizing psychologically as materially. Urban populations, relying on improvised measures and peer-to-peer information networks, effectively became both observers and actors within the crisis, influencing operational decision-making indirectly through social behavior and digital reporting. In conclusion, the blackout's consequences extended beyond technical disruption to encompass social, administrative, and strategic dimensions. Centralized infrastructure proved vulnerable to cascading failure. Public perception influenced by social media emerged as a critical factor in crisis management, and the operational readiness of both civilian and military systems was challenged by dependency on a single grid architecture. The comparative resilience of external examples, such as Ukrainian urban networks, underscored the importance of decentralized redundancy and continuous operational autonomy. Moscow's total darkness served as a case study in the systemic risks of centralized control, informing future policies for energy security, emergency response, and societal stability.